This is Dr.D Govardhan, Professor and Head, Department of Aeronautical Engineering, Ministry of Aeronautical Engineering, Hyderabad. Now the today topic is oscillation of spring and arrangement of springs. Determination of frequency of free longitudinal vibrations by using equilibrium method. Consider a constraint. It may be spring or it may be the shaft, but here we consider spring only, of negligible mass in unstained position as shown in figure A, in which the spring is suspended vertically downward direction by fixing one end at the top and the other end is free. This position is treated as a unstained position of the spring or the constraints. Let S be the stiffness of the constraint, which is equal to defined as the force required to produce unit displacement in the direction of applied force. It is usually expressed in Newton per meter. M is equal to mass of the body suspended from the constraints as shown in figure 2. Then the weight of the body suspended is given by M into G, where G stands for acceleration due to gravity. Its value is 9.81, and delta is the static deflection of the spring in meters due to weight W. X is the displacement given to the body by the external force in Newton's meters. Okay, the figure 2 is representing here now B. The spring is attached with a body having weight is equal to W, which is equal to M into G, which is acting vertically downward directions. Because of its weight, the length of the springs, that is elongates. Assume delta is representing static deflection because it comes to equilibrium position, and hence this W is equal to S into delta. Now in third stage, as a small disturbing force that is applied to the mass M in vertically downward directions to disturb its equilibrium position and release the force. Since when the disturbed force is applied on it, the strain energy or elastic energy that is stored within the body and release the force, this force acts in such a way that it is keeping the body again in equilibrium positions. Hence, while moving towards the equilibrium position, this elastic energy is converted into kinetic energy, and hence it moves upward directions from its equilibrium positions. This process is repeated. That means the body moves up and down with respect to its vertical axis. These vibrations or motions are called longitudinal vibrations. Here X is the displacement given by the body by the external. Now in equilibrium position shown in figure 2, we got W is equal to S into delta, where S stands for the stiffness of the spring, delta is the static deflection. Since the mass is now displaced from its equilibrium position by the X, hence the restoring force is equal to W minus of delta plus X. Where W is treated as positive, it is acting in downward directions. The restoring force is acting upward directions, hence minus of S delta plus X. But W is equal to again S into delta according to the static equilibrium. Hence, the restoring force is given by, on simplifications, we got minus of Sx, which is shown in equation number 1. The accelerating force is equal to mass into acceleration, which is given by m d2 x divided by dt square. And applying equilibrium condition for the system after time t, we have m d2x divided by dt square plus w is equal to minus of s into x plus delta. Since w is equal to s into delta, on simplification we got m d2 x by dt square plus sx equal to 0. It is represented in equation number 3 as d2x by dt square plus s by m into x is equal to 0. This equation 3 is similar to the equation of simple harmonic motions, which is given by d2x by dt square plus omega square into x is equal to 0. And comparing these two equations, we got omega square is equal to s by m. Hence, the time period is given by 2 pi by omega, where omega is the angular velocity, so which is equal to 2 pi divided by s by m, which is also equal to 2 pi by air ms, which is equal to delta by g now. So the natural frequency is given by 1 by 2 pi, which is equal to 1 by 2 pi into under root of s by m, which is equal to 1 by 2 pi into under root of g by delta, where m into g is equal to s into delta. Taking the values as 9.81 meter per second square and delta in meters, and substituting these values in equation number, here assume it is the 5th, we got natural frequency is equal to 0.4985 under root of delta in Hs now. The value of static deflection delta may be found out from the given condition of the problems. For longitudinal vibrations, using fundamentals of strength of material, the stress by strain is equal to Young's modulus. We got Young's modulus is equal to stress by strain, which is also equal to W into I divided by delta A, or delta is equal to W into I divided by E A, which is shown in figure equation number 6 now, where delta L by L is called strain, that is the change in length per unit length. Stress is given by force by area, W by A, and E is representing Young's modulus. It is the property of the materials. It depends on known materials. Delta is representing static deflection, that is the deflection of the spring when the load is suspended and it is in equilibrium condition. W is the weight that is attached to the end of the constraints. L is equal to length of the constraints. E is the Young's modulus of the materials. A is the area of the cross section of the constraints. Okay, by using these fundamentals, we can determine the delta. On substituting the delta values, we can determine the time period as well as the natural frequency of the vibrating system. Alkali springs which are connected in series and parallel. 2 or more alkali springs are used at one place in a system. in engineering field, and arrangement of helical springs may be in series or parallel. Now consider the helical springs which are connected in series as shown in figure A now. In this case, both the springs will be subjected to the same load which is attached at bottom position as shown in figure A now. In series, two helical springs are connected together and one spring is attached at the top. At the bottom position, other spring is attached with the mass. Let S1 is representing the stiffness of the spring, first one. S2 is representing stiffness of the spring 2. Now both the springs may be assumed to be replaced with the equivalent spring of stiffness S such that 1 by S is equal to 1 by S1 plus 1 by S2. Since S1, S2 is representing the denominator now, so that values now become S1 plus S2 divided by S1, S2 in simplifications. Similarly, in other arrangement and parallel method. In another method, the two springs may be kept parallel to each other by attaching each end of spring to the ceiling, that upper part, and lower part is again attached to the common platform, that is a rod, and the weight is attached to it. In this arrangement, the load is distributing among the two springs. The magnitude of load that is distributed depends upon the stiffness of each spring. Now, in this arrangement, assume these two springs are replaced with the single spring, whose equivalent stiffness can be determined by using the relations S is equal to S1 plus S2. After obtaining the stiffness of the springs, we can determine its time period as well as the natural frequency of vibrating systems. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.